We're first going to do an introduction to all of the variables associated with the gas laws, and then we'll talk about Boyles, Charles, and Gay-Lussac. Before we talk about the individual gas laws, we need to talk about the variables that are associated with them. The first variable is pressure. Pressure is often represented by the letter P and is a result of the particles colliding with the sides of the container. They bounce off the container frequently. We typically measure particles in ATM or atmospheres. It is not limited just to ATM though. It can also be measured in torrs, millimeters of mercury, kPa, or PSI. These in the bottom right-hand corner here are all the standard pressure units that we could have. So if something indicates it's a standard pressure and it's in ATMs, you would use 1. If it's torrs or millimeters of mercury, you would use 760. If it's kPa, you would use 101.3. And if it's PSIs, you would use 14.7. Our next variable is volume. Volume is represented by the letter V. Volume is the space occupied by the particles, and it is the size of the container. The most common volume that we use is liters, or capital L. You can also use a milliliters or centimeters cubed. The common conversions are down here. Keep in mind that 22.4 liters is always equal to 1 mole, 1,000 milliliters is always equal to a liter, and 1 milliliter is always equal to cubic centimeters. The big thing to keep in mind when you are doing units with volume is that both units of volume have to be the same. Our next variable is temperature. Temperature is represented by the letter T. It is the average kinetic energy of particles, particle speed. The higher the temperature is faster the particle. When you are using temperature with gas laws, it must always be in Kelvin. Kelvin is represented by a capital K. If the temperature was given to you in Celsius, you must convert to Kelvin by simply adding 273 degrees. If they ask for a standard temperature, the standard temperature for Celsius is 0 degrees, and the standard temperature for Kelvin is 273. Our next variable is amount. Amount is represented by a lowercase n. It is the number of particles in the container. So the more particles it has, the more moles the substance has. Since amount has to be in moles, if the given was given to you in grams, you would need to convert. Just a reminder that 1 mole is equal to the molar mass of something, and 1 mole is also equal to Avogadro's number, which is molecules, particles, or atoms. But N must always be in moles. Finally, our last one is rate. Rate is represented by the capital letter R. It is the work done by the gas. There are 3 common rate conversions, okay? In order to know which rate to use, you would need to look at the pressure. If the pressure is in kPa, you would use 8.314. If the pressure is in ATM, you would use 0.0821. And if the pressure is in torr or millimeters of mercury, you would use 62.36. You do not need to necessarily memorize these, but this is a good thing to know, and you will start to become more familiar with them the more problems you do. Now let's get into our gas laws. The first one we're going to talk about is Boyles. Boyle's law states that if the volume of the container decreases, so it goes down, that means the pressure in that container is going to increase. This also indicates that temperature and amount are constant or are not changing. Since one goes up and the other goes down, they are inversely proportional to each other. We can see the equation for Boyles here. It is P1 times V1 is equal to P2 times V2. P1 and V1 are your initial pressure and volume, and P2 and V2 are your current pressure or your final pressure and volume. The initial and the current units must match. So if one pressure is in ATM, the other must be in ATM. If one volume is in liters, the other must be in liters. They must match. This is our equation to show that pressure is proportional to the inverse of volume, and just a graphical representation. As volume increases, then pressure goes down. Okay. You're now going to want to pause the video and gather your materials to do some practice Boyles problems. You're going to need a calculator, a periodic table, and something to write with. All right, let's go ahead and do a couple of practice of Boyles problems. The first example is a balloon with a volume of 5 liters is filled with a gas at 2.0 atmospheric pressure. If the volume is reduced to 2.5 liters, what would the pressure of the balloon be? So let's go ahead and list our variables. Okay, so we know it's Boyles, so we know it's going to be P1, V1, P2, and V2. So our first volume is 5 liters. We can fill that in. Our first pressure is 2.0 atm. Our second volume is 2.5 liters. And we're solving for our P2. We know our equation is P1 V1 is equal to P2 V2. And now we can plug everything in and solve. So P1 is 2, V is 5, P2 is our x, and V2 is 2.5. So 2 times 5 is 10, and then we have 2.5x. We're going to divide each side by 2.5, and now x will equal 4. So since our first pressure was in atm, our second pressure will also be in atm, so our final answer then is 4 atm. Go ahead and check your work to see if it matches mine, and we'll try a second example. All right, our second example is up on the board. We know it's still Boyles, so it's going to be P1, V1, P2, V2. It says a gas occupies 11.3 liters, so we can fill this in. We know the pressure is 0.860 atm. It says what is the pressure of the volume, so we're solving for P2, and our new volume is 15.0 liters. Now keep in mind we did solve for P2 in both equations, but you could solve for any of the variables. So we know it's P1, V1, P2, V2, and we can fill in our missing numbers. 0.860, 11.3, P2 is our x, and V2 is 15. So we have 15x, and then 0.860 times 11.3 is 9.7. And then we divide each side by 15. And x is 6.47. The first pressure is in atm, so we know the answer will be also in atm, and 6.47 atms is our final answer. Charles' law states that if the temperature of a gas increases, the volume of the gas also increases. So Charles's law is the relationship between temperature and volume. Pressure and amount are constant and are not used in this equation. Since Charles's law states that temperature increases, volume also increases, this means that temperature and volume are directly proportional to each other. If one goes up, the other one will also go up. We can see here Charles's equation. It is V1 over T1 is equal to V2 over T2. Once again, as a reminder, your volume units must match. It can be liters or milliliters, but they must be the same. Your temperature must also be in Kelvin. If it is given to you in Celsius, you need to add 273 to get your Kelvin. We can see that volume is directly proportional to the speed of the particles. Faster particles need more space. And we can see our graphical representation. As the temperature increases, the volume will also increase. You're now going to want to pause your video and gather your materials to do some Charles's Law practice problems. You're going to need a calculator, something to write with, and perhaps a periodic table. All right, we're going to do a couple of practices for Charles. Just a reminder that Charles' variables are V and T. So we have V1, T1, V2, and T2. And then we can fill them in as we read. An expandable piston holds a volume of 15 milliliters at 293 degrees Kelvin. The temperature of the piston is reduced to 215 Kelvin. What is the new volume? So a couple things to keep in mind. When you're doing Charles's problem, you want to make sure the temperature is in Kelvin. We're already in Kelvin. And you want to make sure your units for volume are the same. It doesn't matter if it's milliliters, liters, cubic centimeters, or anything else. But our final answer will also be in milliliters. So we know it's V1 over T1 is equal to V2 over T2. V1 is 15, T1 is 293, V2 is X, T2 is 215. You can now cross multiply to solve. So 15 times 215 is equal to 293x. So 15 times 215 is 3,225 is equal to 293x. And we're going to divide each side by 293. So our x will be 11.0. The first volume was in milliliters, so our second volume will also be in milliliters, so 11.0 milliliters. Take a second to check yours to see if it matches mine, and we'll do one more Charles problem. So once again, we know it's Charles, so we can go ahead and list our variables, V1, T1, V2, and T2. We know the volume is 852 milliliters. We know the temperature is 25 degrees Celsius. We don't want Celsius, so we have to convert to Kelvin by adding 273. We are looking for the final temperature in Celsius, and our final volume is 945 milliliters. So we can plug it into our equation. 852 over 298 is equal to 945 over x. You can now cross multiply. Okay, we'll flip that to green. Okay, so 852 times x is equal to 298 times 945. So we have 298 times 945, and we get 281,610 is equal to 852x. We're going to divide each side by 852. So then our final answer will be x equals 330. Now it does say it wants the final answer in Celsius. If it wanted the final answer in Kelvin, we could keep it at 330, but since it wants Celsius, we need to subtract 273, and we get 57.52 degrees Celsius.
Gay-Lussac's law states if the temperature of a gas increases, the pressure of that gas will also increase. So Gay-Lussac's is using the variables temperature and pressure, which means volume and amount are constant. This means that temperature and pressure are directly proportional to each other. We can see the equation here. We can see that it is P1 over T1 is equal to P2 over T2. Your pressure units must be the same, whether they are ATMs, millimeters of mercury, torr, or something else. Temperature, once again, must also be in Kelvin. If it's given to you in Celsius, you must add 273 to get Kelvin. We can see that pressure is directly proportional to the speed of the particles. Faster particles are going to collide with the container more often. And we can see our graphical representation. As temperature increases, so does pressure. You now want to pause the video and get ready to do some Gay-Lussac practice problems. You're going to need a calculator, something to write with, and perhaps a periodic table.
All right, we're going to do a few Gay-Lussac example problems. Just a reminder that Gay-Lussac's variables are pressure and temperature. So we can go ahead and start by listing our variables, P1, T1, P2, and T2. I highly recommend you list your variables whenever doing any gas laws. So let's read the problem and fill in what we know. A steel container holds a gas at 5 degrees Celsius. So we know it's 5 degrees Celsius. We also know that it must be in Kelvin, so we're going to add 273 to get 278. Our pressure is 101 kilopascals, and the temperature of the container is increased to 100 degrees Celsius. Once again, it's Celsius, so we need to add 273 to get to Kelvin. We want to look for the new pressure. Since the first pressure was in kPa, this one will also be in kPa as our final answer. Our equation is P1 over T1 is equal to P2 over T2. We can now fill in and solve. So we have 101 over 278 is equal to x over 373. You're then going to cross multiply to solve. So 101 times 373 is equal to 278x. So 101 times 373 is 37,673 is equal to 278x. We divide each side by 278. And our final answer will be 135.5. And since our first unit was kPa, our second unit will also be kPa. So go ahead, check yours, and if you have any questions, check in with your teacher. Let's try another Gay-Lussac example. Once again, it's Gay-Lussac, so we know our variables are pressure and temperature. We can make our list. P1, T1, P2, and T2. Okay? So it says if a gas is heated from 231 degrees Kelvin to 315. So we know those are our temperatures. So 231 Kelvin and 315 Kelvin. They're already in Kelvin, so we don't need to add 273. And the volume is kept constant, so it's not in this problem. The final pressure, or it says what final pressure would result. So our final pressure is going to be our X, and the original pressure is 621 millimeters of mercury. Since the first one is millimeters of mercury, this final answer will also be millimeters of mercury. Our equation is P1 over T1 is equal to P2 over T2. So now we can fill them in. So 621 over 231 is equal to X over 315. You can now cross multiply to solve. So 621 times 315 is equal to 231x. So 621 times 315, 195,615. So 195,615 is equal to 231x. You're going to divide each side by 231 to get x by itself. And x will now be 846.82. And our unit is going to be millimeters of mercury. Go ahead and check in with your teacher.